So, our galaxy is not alone. There are, according to the mighty Hubble Space Telescope, there are several 100 billion other galaxies visible in our universe, at least. So let's talk about those other galaxies. And so, what do we do in science? Well, we look at the universe around us, we observe it in detail, mathematical detail, we look for patterns, we try to then develop hypotheses and theories to explain those patterns, we put them to the test. That's science. So, other galaxies, we look for patterns. We find that galaxies fit into their three major types of galaxies. First of all, you got galaxies like ours, spirals. There are elliptical galaxies, ellipticals, and then there are irregular galaxies. Most galaxies, slightly majority just in general, appear to be spirals. Ellipticals are, I don't know, 30-40% of galaxies exact, depending on how you count it. Irregular galaxies are not so many, 10% or less, depending on exactly what galaxies we're sampling here. So what are these galaxies like? Well, the first thing we notice is that spirals, okay, like our Milky Way galaxy, have two main types. They have their disk, and they have their spheroidal population, spheroidal stuff, which means the bulge, and halo. And that's spiral galaxies. The disk, which has young blue stars, and then the spheroidal stuff, which only has the older, orange and red stars. When I look at ellipticals, what do I see? An elliptical galaxy is basically like a spiral galaxy with no disk. It's basically just a spheroidal population. Just a spheroid. So that means elliptical galaxies are kind of blobby in shape, sometimes football shaped sort of thing, kind of a little more amorphous. They're going to have like kind of a bulge, which then blends out smoothly into a halo. They may have globular clusters and things around it. As they get far away, it's hard to tell for sure, but that appears to be what they have, and they tend to be orange-red in color. So that's kind of interesting. Irregular galaxies tend to be, they're not as well structured, not well structured. But in terms of color, they tend to look blue. Blue means they have hot stars. Hot stars are young. Hot stars don't get old. So that means they have young stars forming basically now, currently. If I see a blue star, nice, hot, supergiant star, gosh, well, those things don't last very long, so it must have formed within the last couple million years. There must be ongoing star formation taking place in there. This is interesting. Spirals, ellipticals, irregular galaxies. Ellipticals are basically just what happens with a spiral if you take away the disk. So, why? Okay, three categories of stars, three categories of galaxies. Let's do another clue. Another clue is that galaxies, scattered throughout the universe, but they're not totally irregular in how they're scattered throughout the universe. There are clusters of galaxies. Think about this. Okay, so it takes our sun 200 million years to orbit around our Milky Way galaxy. Well, now you've got clusters of galaxies where you've got whole galaxies orbiting around each other, and orbits may take 1 billion years. I mean, this is a very long sort of thing. Galaxies, they're bound by gravity. They're orbiting each other. When we do this, we see hundreds or thousands of galaxies all orbiting around each other. And in places where you've got galaxies orbiting around each other tightly, elliptical galaxies are more common. Ellipticals are more common in clusters, particularly rich clusters. Well, that's an interesting thing. So, if I was in the spaceship, I'm in a starship flying out there, different galaxies, want to find other civilizations, I'm not going to look in ellipticals because, okay, they have only the old stars. So they formed the spheroid, they formed that generation of stars, and then no disk. And the disk is where ongoing star formation takes place. We're a disk star, and there's a very good reason for that. You look in here, what are we made of? We're standing on the Earth. The Earth is made of iron and nickel, and has a lot of silicon and carbon and oxygen and nitrogen, and all these elements require the star gas star cycle to be running to create all these sorts of things. In an elliptical galaxy, no. You formed your generation of stars. There they were. They're nice. They're lovely. That's it. when we look at when we look at elliptical galaxies, they're filled with very hot gas. Very hot gas, very low density gas, not the sort of gas that's ever going to form any stars anytime soon. When we look at a spiral galaxy has a disk which has the whole star gas star cycle in it, which means some hot bubbles and some warm atomic gas and then some cold molecular gas where new stars are forming and all this. You don't see that in elliptical galaxies. So the question is why? Why do we have these two different types of galaxies? Why do we have spirals and ellipticals? Right now, astronomers don't know. There are several different ideas. There are people who are doing research. One idea is that suggests that basically every galaxy is born as a spiral, but what happens is when spiral galaxies smash into each other, when they collide with each other, well, the stars kind of go right past each other, since galaxies are mostly empty space, but the gas from this galaxy collides with the gas from that galaxy and kind of gets left behind, and so that strips away the disk. So one hypothesis is that all galaxies are kind of born as spirals, but then when there are collisions in rich clusters where galaxies are packed densely together, then the disks get stripped out of galaxies, and then what do you got with the galaxy when you strip away the disk? Well, that's an elliptical. There's one hypothesis. Another hypothesis is no, that the galaxy is either a spiral or an elliptical from the beginning, and that it has to do with how it formed. Like if there's more spin to this protogalactic cloud, then this spin will cause it to organize itself into a nice, well-organized disk. But if it doesn't have quite as much spin, just through random chance, some protogalactic clouds have more spin, some others have less. Maybe that would mean in this case that having less spin means, okay, it's all going to form the stuff at once. It's not going to form a disk. Your high-mass stars go supernova, they blow the gas away, and that's the end of it. I don't know. They're definitely doing research, whether everybody's in a spiral and then turned into ellipticals, some of them, or whether, no, it has to do with the details of things. We really don't know. There's a lot of ongoing research into why we have these different types of galaxies. Irregular galaxies tend to look like things where either they're nearby and recent, and therefore they're not, they're colliding with something, so that's kind of messed them up. Or maybe they're very, very far away. Maybe we're looking back in time toward the early days of our universe where they haven't really had a chance to organize themselves into a regular spiral or elliptical yet. There's a lot to be figured out in terms of the types of galaxies and why we get the types of galaxies. The different types of galaxies were first studied by the greatest astronomer of the 20th century, Edwin Hubble, great American astronomer. He was the first one who really proved that other galaxies are other galaxies. At first, astronomers kind of thought, well, maybe that's a cloud of gas relatively nearby. No, he was able to establish that no, they really are far away. They're whole other Milky Ways, whole other island universes was kind of the old term for that by themselves. So Edwin Hubble proved that other galaxies are other galaxies. Galaxies exist. And so he studied them, kind of came up with our classification system, spiral, elliptical, that sort of thing. And he also studied the motion of galaxies, and he discovered an amazing pattern in the motion of galaxies. Studied motion. And what he found is a relatively straightforward thing. He found that the farther away a galaxy is, the faster it's moving away from us. Almost all the galaxies in the universe are moving away from us. Only a few very nearby ones happen to be moving towards us, like Andromeda. But other galaxies are moving away from us, and and the farther away from us, the faster they're moving in a very linear relationship. If I plot out, here's the distance to other galaxies, and here's their speed, say in kilometers per second, and here's their distance in megaparsecs, then what I find is that galaxies, there's some scatter around here, but they kind of fit a nice straight line. The galaxies which are twice as far away are moving away from us twice as fast. So we call this Hubble's law. Hubble's law, and it says the velocity of a galaxy is equal to Hubble's constant, h sub 0, times its distance. Right now, h0 depends on the units. h0 is estimated to be about 70 kilometers per second per megaparsec. So this means that if I have a galaxy which is 1 megaparsec away, it'll probably be moving away from us at a speed of about 70 kilometers per second. Let's do a little math. Okay, so here's the equation. Velocity equals h naught times d. And so h naught is roughly 70 kilometers per second per megaparsec. So if d equals 1 megaparsec, then velocity equals 70 kilometers per second per megaparsec times 1 megaparsec equals 70 kilometers per second. If, on the other hand, I have a galaxy which is 2 megaparsecs away, then velocity would be 70 times 2 equals 140 kilometers per second. If I have a galaxy which is 3 megaparsecs away, 210 kilometers per second. So there's this relationship between speed of a galaxy and distance. Edwin Hubble discovered our universe is expanding. This is what we mean when we say our universe is expanding. I'm not expanding, you're not expanding, the Earth is not expanding, the solar system is not expanding, the Milky Way galaxy is not expanding. What's expanding is the distances between distant groups of galaxies. As our universe is still spreading out due to the Big Bang, which, gave this momentum, everything's moving away from each other, and it's still going on today. This was the first evidence that led people to this idea that our universe had a beginning, a point in time at which it came into existence, was this sort of thing here, the expansion of the universe, the Hubble's law, the motion of all galaxies are all spreading out, moving away from each other. Now, we're not at the center of this. No galaxy's at the center. No matter wherever you are, from any galaxy, you would see the same basic pattern. You would see all galaxies moving away from each other, and the farther away you are, the faster they're moving away from each other. So there's this overall pattern to things. And we can use this to estimate the distance to very distant galaxies as well. If I see a galaxy and I say, I want to know the distance, well, distance, reorganizing, is velocity over h naught. So if I see a galaxy which is, suppose it has a velocity of 280 kilometers per second, I can then estimate that, 280 divided by Hubble's constant, which is 70. This must be 4 megaparsecs away from us. So there's kilometers per second per megaparsec. The kilometers per second cancel out. And so this allows us to establish distances where things are really far away. For closer galaxies, Hubble used Cepheid variable stars. They kind of allow us to measure the distances to other things in the universe. A Cepheid variable star is a big red giant star that gets bright and faint and bright again in a regular cycle. And what was discovered is the astronomer Henrietta Leavitt discovered that there's a straightforward relationship between how long it takes for a star to get bright and faint and bright again, its period, and its total peak luminosity. So Edwin Hubble looked out there and he looked at the Andromeda galaxy and he saw that, wow, there are these Cepheid variable stars in Andromeda. And they take a very long time to go from bright to faint and bright again, basically a whole month. And so then he would see them for a few days and then they'd faint and he couldn't see them again. And a month later he'd see them for a few days. And so he said, wow, since there's a very long period to these Cepheid variable stars, they must have a colossal luminosity. On the other hand, I can barely see them. And Edwin Hubble was using the Mount Wilson Observatory down in California, absolutely an amazing telescope, the biggest one in the world at the time. And he could barely see them, and yet they must have a colossal luminosity since they're taking such a long time to go from bright to faint to bright again. That must mean they must be amazingly far away. That's how Edwin Hubble proved that Andromeda really was millions of light years away from us, was outside of our galaxy, really was a whole galaxy in and of itself. And so that's Hubble's law, and this is the first hint that there might be something called the Big Bang lurking at the beginning of time, and we'll talk more about that later.